interests are on sensor localization and navigation, generation of 3D high-definition mapping products, artificial intelligence and intelligence systems, collaborative platform mapping, and rapid computation methods. He is a fellow of the International Society for Photogrammetry and Remote Sensing and has served as president of the ISPRS Technical Commission 4 on digital mapping and geodatabases, and as a co-chair of the ISPRS Intercommission Working Group 1 divided by 5B, Unmanned Vehicle Systems, UVS sensors and applications. Currently, he is co-chair of the ISPRS Intercommission Working Group 1-2, Unmanned Airborne Systems and Small Multi-Sensor Platforms, Concepts and Applications. This is just from my side, and I would like to hand over the words to Professor Armenakis. Thank you for coming, for joining us, and Kostas, the floor is yours.
Thank you very much for the kind introduction, Lena, and thank you very much for the invitation to present some of our work. Before I start, I'd like to say that our thoughts are with our colleagues, the families, and the people in the war zone, and let's hope that peace will return as soon as possible everywhere. My presentation today is on geospatial information extraction from Earth observation imagery using deep learning approaches. This is the work is also in this work have contribution from my students, Somia, Evangelos, Agatha, and Mahia. The outline of the presentation will include, why we're doing what we do, machine learning models, machine learning versus deep learning, the Earth observation image properties with respect to deep learning, and then, excuse me, we're going to have to discuss some examples of using deep learning in our projects and in our research. One relates to tree species classification, where we use supervised learning and transfer learning. The other relates to change detection with some examples of some work on supervised and semi-supervised learning. And then we have two examples where we started using and experimenting with reinforcement learning. One is on the UAV flight path, and the other one relates to image segmentation. Our objectives, of course, the objectives of the society and the people working in the area of photogrammetry, remote sensing, and geospatial information science is the extraction of geometric, thematic, and physical information about the Earth and landscapes. And we use, of course, aerial, satellite, and low altitude images. The challenge has always been there, and how we can do this work faster and more accurate. So essentially, we're working on the development of automated algorithms to extract accurate geospatial information from image data. The machine learning models we have experience and we are working on, and relates to the learning, right? So what is the learning? The learning relates to the transferring experience into expertise or knowledge through some optimization criteria. There are 4 algorithms of machine learning. We have the supervised, the unsupervised or predictive, the semi-supervised, and the reinforcement learning. Some of them require labeled data, while, for example, in reinforcement learning, the system, the agent, learns through interaction with the environment. On the top here, you're going to see an example of inductive learning, and this is what we usually do in the supervised learning, that we have labeled samples, we have a prediction model, and then we have predicted labeled data. And after we do the training in the prediction model, we enter the unlabeled data and we do the generalization. On the second figure here, we have a form of transductive learning, which is a form of the semi-supervised learning, where we work with both labeled and unlabeled data. And using this combination, we come up with our prediction model, and the prediction model relates results on the learning model, and then we predict the labeled data. Now, deep learning versus machine learning, right? We all have experience with machine learning, and the difference here is that in the machine learning, we have the input, we have feature extraction, and we do the model and then the output. While in the deep learning, we blend feature extraction and model, and then we get the output. Now, what we have seen here in the performance and the amount of data, we have seen that the deep learning performance, right, it's surpasses the machine learning performance. However, the amount of data that we need, it's quite significant for our training purposes. Now, what is the basics of the deep learning and the convolutional neural network? Essentially, we have our input that goes through the network through a forward propagation, and this is the linear propagation where we have our input, our weights, and our convolution, and of course we get the output, including our bias. Then we estimate a loss function. This is our optimization, and the optimization is determined by the output of our model and the ground truth, and then we do through the back propagation, we adjust the weights, and until we achieve accuracy and loss levels, satisfactory accuracy and loss level. So our data sets, right? We need the data sets for training, data sets for validation, and of course we need the data sets for our testing. Now, when we use Earth observation images, we observe that the images we recently use are mostly high resolution. They have 3 or more bands. They cover large areas, and they have more classes that they need to be determined. So they're not simple laboratory images that they may have 2 or 3 objects, let's say, of an office, that they might have a chair, a desk, and a cup. And what we are looking, and this is what we have to keep in mind when we select our approaches, is we try to achieve high semantic and geometric accuracy, and this relates to the pixel-wise classification, and of course to preserve object boundaries or do object extraction. As well as we have in our system, we have high reliability, and especially in the supervised learning, we have to have a large number of labeled data. So our first example relates to the 3-species classification, and for that we use UAV, RGB, and multispectral data. And the idea is to develop a classification model based on convolutional neural network to identify individual 3 species in a complex mixed wood stand. And this is from RGB in this case, data collected over a 3-year period. We also we also want to assess the transferability of the developed classification model to different size, and also to incorporate single date multispectral data from UNV and compare the results with the RGB images. For this methodology, we experimented with 2 CNN architectures. One was the residual net, ResNet 50, and the other one was the dense net. In the ResNet, we used some knowledge transfer, and then we did the training. And as you see, of course, this is building, the ResNet is based on residual learning, right? So we have, that skip function here, while the DesNet is based on dense blocks that we have interconnected links. And the fact that we have interconnected links is we wish, because the network is become dense, that means we have a large number of layers. We want to be able to transfer, features from earlier steps to the next steps, but also this helps the propagation, the back propagation. The test site was in Ontario, and this is where you have a predominant species. This is a list of the trees that we had to detect. Images acquired in 3 years, and the test area is about 20 hectares. And you can see here, what we try to do here is we collect the data with the leaves on and different seasonal conditions, so to have different density and greenness, and as well as to have different, to have illumination variability. So you can see here, we have the RGB camera and we have the multispectral camera. The preparation of the data, as we said, that was a supervised learning. So we generated ortho images, and then we did the tree crown delineation, and then we extracted the individual tree crowns that they use for the annotated data as input to CNN for training. And this is an example of the tree crowns, and you can see on your right the composition of the training set. So you can see the species, you can see the numbers of trees using on the training, and the number of training images. And of course, the segmented labeled trees were split on the training set, which is 50% for training, 50% for validation, and then we had the prediction test. Now, the results are, you can see they were expressed in the usual metrics of recall precision, F1 score, and accuracy. And, there was various levels obtained for each individual tree. And overall, we have, satisfactory F1 score and accuracy. Here on the bottom, you can see, bottom left, you can see the detected trees, the detected species, where on your right, you can see the yellow are the correctly classified trees, and the reds are the misclassified trees. We also experiment with the transferability, and the reason is we experiment in 3 sites, and we want to see, if knowledge gain or training obtained in one side is applicable in the other side. So first of all, we had, site 1 that we test the data. Then site 2 had the similar condition to site 1, while site 3, they were different. So let's say the tasks, were the same. However, the environment was different. And here you see what we mean with the transferability of knowledge. In site 1, you can see, we had the training, and then we're predicting in the same area. While as we move a different site, we can have, for example, here transfer learning model. So we have some training from site A, some training from some data from site C, and then we try to detect prediction, to do prediction on site C, for example. And also here we have, let's say, a composite model from, let's say, site A and site C, and try to predict site C. So these are various combinations, and here we can see, the various recall values for the different trees. So still, this is a work in progress, and this is very important because it's very time consuming when we move from site to site, as in forestry, try to create annotated data for the label. We also try to use, we started working on multispectral images. We had the Mica Sense Red Edge M, and we will try also as well here to do knowledge transfer from the RGB to MS data, and this is work in progress, as well as we also in the progress now of doing ensemble techniques, and that is the stack generalization, where, let's say in our case, we are having two models. So one model is the CNN from the RGB data, well, the second model is the CNN from the MS data, and then through a meta-learning system, we can try to improve, especially the results from the MS data, where we had lower resolution data, and we had some issues of the co-registration of the multispectral channels. The other application we work on was about on-change detection using deep learning. And of course, change detection process, everybody is familiar with that. We have multi-temporal images. We try to identify changes, spatial changes, type of change, and also timestamps, so where, what, and when. And of course, we have to address both the actual changes and the apparent changes. For example, we have different viewing geometry, different radiometry, misregistration, different lighting conditions. Now, we work here, on the change. We have, the approaches could be a post-classification change detection approach or a direct change detection approach. And we experimented with a direct change direction approach using deep learning. Again, for that, we acquire training data from very high resolution images. The spatial resolution vary from 30 centimeters to 1 meter. We had 10,000 training images of 256 by 256. And you can see the large amount of training of annotated data that we need. And we had 3,000 images for validation and 3,000 images for test. And you can see here, the first column is, let's say, time 1, second column is time 2, and you can see here the masks for the training. You can see here we have also different coverage. That is a snow area in here, but we have no snow in the other picture. We experiment on how to improve the change detection by using semantic edge enhanced UNet and UNet plus architecture, and I'll come why we selected the UNet. And also the training approach has been improved. The robustness of the training approach has been improved using registration errors, and also we try semi-supervised training approach using consistency regularization. We use the UNet approach. This is the UNet that we have. As you can see, a contracting leg and also an expanding leg here. And the whole idea, remember, we mentioned that we have to, in our case, to maintain the spatial properties of our images. And, usually the CNN, they reduce the resolution of the images. So here we have, a reduction of the resolution, and then we have an expansion to come back to the resolution. So the expanding and contracting path and expanding path. And you notice here that we have also skip connections, and the skip connections are the various levels. And the skip connections, essentially, they transfer, feature maps from the contracting path to the expanding path. And this is in order to maintain, information from previous steps. And the difference between UNet and UNet++ architecture, here you can see that instead of having only skip connections, we have also, blocks. So that means we transfer, layers and the convolutions and the activation functions, from the contracting path to the expanding path. So essentially, we try to maintain the information as well as the resolution. Now, in this approach, we thought to improve the change detection by incorporating semantic edges. So the semantic edges were incorporated, as you can see, at a different level of the network. So we had the UNet, and then we have the edge detector that was applied, at the input and also at the output. And the same thing also with the UNet. Again, we apply the edge detector. And when I say edge detector, we are talking about semantic edge detector. So we don't refer, of course, to just edges defined, let's say, by shadows, but actual edges, object edges. And for the semantic edge detector, we use the dense extreme inception network for edge detection, the DEXINET. And you can see the DEXINET, again, is a form of contracting and expanding. And also we see the contraction here, but also we have, skip connections. And the train is very interesting here. We did a sort of knowledge transfer as we did the training of the edges on the ISPRS Vikingian data set. This is an overview of the semantic edge detector and misregistration. So you can see we use the UNet and UNet++. We enhance with edges, and the edges came from the DEXINET. And then we use the change detection on the original data with edge enhancement, and then the change detection where we include misregistration errors, and the misregistration errors, we create additional data set where we apply rotation and affine, and then we go the go through the process and then the evaluation. This is an example that we have, time 1, type 2, and then the ground truth. And this image, for example, has been slightly, rotated and also subject to a fine transformation. And then we use a new data set to assess the misregistration. The evaluation metrics we use are the usual: precision, recall, F1 score, and also we use the intersection over union. And these are some of the results of them, where you have, image at time 1, image at time 2. This is the UNet++ with Lovich hinge loss function, no boundaries. This is the binary entropy. And then this is with boundary, and so on and so forth. So these are the results, and you can see here the label on the colors, true positive, true negative, false positive, false negative. So you can see that the results are acceptable. We also quantify our results, right? So the various results we have here on the left, you see the UNet with the original data set. Here is the UNet, UNet++, UNet, and then the various runs we did was with different loss functions. So we have here the binary cross entropy with dice coefficient loss function and with Lovich hinge loss function, and as well A, B, and NB refers to added boundaries and non-boundaries. And you can see here that we have better performance when we have the UNet and when we use the boundary information. And the same thing happened when we use when we assess the robustness to misregistration error. Again, you see the various cases. Again, precision, recall, F1 accuracy, and ROU. And we see, and of course, these are the different loss function with or without boundary plus the misregistration errors. And we can observe an improvement of 1 to 2%. And also, we can see observe an improvement in the presence of added misregistration error up to 5%. So both the semantic edges and the misregistration training improve in the change detection results. Because we had difficulties of getting data in a number of occasions, we also did some experiments using semi-supervised training approach, and that was because of the lack of labeled data, especially in other areas, and the large number of available unlabeled data. So in the semi-supervised approach, we have the change mask, and also we have the pair, and from two different epochs, and then we use the student-teacher approach, where and then we have the prediction, and at the end we have from the image pair, and we have the unsupervised loss, and then from the change mask we have the supervised loss, and then we get the weighted mean for the total loss. From the student, you see we have a transformation of the data, right, in order to bring the data in the same form that we apply prior to getting to the network, and then the transformation is applied to the teacher after the network. And we have a control between student and teacher. We control the weights through the exponential moving average. So essentially, we try to control the weights in order to train the student based on the teacher input. The results in the hypothesis we had, right, we were expecting as the number of training samples decreases, because this is the whole idea of the supervised and semi-supervised training, that as the number of training samples were decreased, we hope that the semi-supervised performance will exceed the supervised performance. However, we saw that only in the case where we had, a 2,500 label triplets, and we had 7,500 unlabeled. So we saw only in this case here where the semi-supervised case exceeded the perform better. So we are still working to improve the situation. And this is, your some prediction examples from the semi-supervised training. We have, the two image set, and we have the ground truth, and then we have, the supervised, how many samples we had, semi-supervised, how many samples, and you can see that in this area, 500 and semi-supervised, and the semi-supervised column here, that we had the better data. The other projects that we use was we started experiment using reinforcement learning, and the motivation of that is for the photogrammetric operations. We need an experienced pilot, and we want to see how we can overcome, errors in the paths of the UAV by the pilot. So the question is, can we develop methods for autonomous trajectories? Reinforcement learning essentially is learning by experience. So what we have here, we have, the environment. Let's say this is an example the dog owner and the dog. The dog owner, throws the stick. The dog has an agent, either catches or not catches the stick and brings it back. And these are the actions. So based on the actions, we provide rewards. So essentially, we train the agent to reach predefined goal in order to maximize the rewards. And then after the training, we apply the optimal policy on unseen similar environments. So same thing when we have a UAV and the images, we have the environment, the UAV is the agent, and of course the camera takes an action, right? The action changes the state, but also based on the action through an optimization function, we assign rewards to the agent. Our experiments were on following a trajectory and especially do a feature following, and this feature following relates to, let's say, the central of the street. Let's say if we want to apply to study change detection, we want the UAV to follow the same path at the second time. And this is the reinforcement learning approach that essentially we learn the policy and then we use the deep quality network, the DQN, as a learning strategy. And during the training, the agent, the UAV or the camera receives the rewards, and the rewards is based on an optimization function. And of course, the highest is value of that define the optimal actions to be taken. So, if the action is optimal or within our specification, then the proper rewards are given. So essentially, we have the UAV. This is the motion of the UAV, and this is supposed to follow the central line of this road. Actually, is the runway in the airport. So, the question is it following properly the central line? So every time, it moves left or right, we have a new state of the UAV, but also based on the deviations, then we assign rewards. And this is the DQN implementation. First of all, we have step one, which is the training, as you can see. So the observation is if we follow the center line, we get rewards. This is your Q value estimator, and this is your actions. And after the training, where we have developed, the state policy reward system, then in step two, we have the deployment, where the agents train knowledge on best actions can be applied to an unseen and similar environment. And this is the whole idea. Here is to navigate from one point to the other and follow the center line of the, keep the center line at the center of the captured images. And you can see here, the yellow is the road center line. This is during the training process, and this is what we want to have at the end. So this is before the training, that you can see that the center line is off, is not in the center. Well, after the training, we expect to have the center line in the center of the image. And this is an example of we can have before training and how it deviates. So you can see here deviation, and then the whole idea is to follow the center line. And you can see here how the center line is moving or going off. And after the training, how the UAV maintains the center line right in the center of the field of view of the RGB image. The last example that we have been doing is we look at semantic segmentation from mobile sensor using reinforcement active learning. The reason again for the semantic image segmentation using supervised learning methods, we require a huge label data set. And And the reason is because we want to have pixel-wide annotation, which are, extremely time-consuming to have. So the challenges, of course, are to acquire pixel-wise label, which, as I mentioned, is expensive to have, and also to have realistic data sets, that our realistic data set have unbalanced segmented classes. So definitely we have some classes that they are underrepresented. So what we are trying to do here is, by using active reinforcement learning, and I'll explain what we mean active reinforcement learning. Essentially, we have an operator, a knowledge expert that contributes to the training of the unlabeled data. So by using active reinforcement learning, we wish to, or we would like to, decrease the amount of data sets and minimize the operator's effort, and to improve the performance of the segmentation network of the underrepresented and critical classes by optimizing the mean IQ by the deep query network. And this is, the methodology is a bit complicated, I guess, diagram here, but essentially is a loop based on what we said. So we have the state, right? So the state is entered to a segmentation network, right? Together with some samples from the unlabeled data. With the states, we build the states and we build an action pool, right? Because we need actions. And then we go into deep query network. So that is the reinforcement learning agent which develops the policy. Policy relates to the activities that the agent takes. So based on the chosen action, we go into the labeled data, and then we have the expert knowledge that labels the data and makes correction, and that the new data are added to the label set, and that helps the training. And after the training, of course, we do an evaluation, and we have the rewards that as well go when we compute the reward base on the deep QN. So essentially is a loop that we start the process with building the states, build the actions, develop the policy, right, which selects which action, reserves a reward. If things work properly, with the help of the expert, we put unlabeled data into the labeled data set. So we increase the labeled data set. So that means helps the training. And at the same time, we sample unlabeled data for this process. Now, in closing, we have seen the convolutional neural networks have grown in popularity in our community. Why? Because it's easy to train, right? If we have data, have excellent generalization capacity, and also have state-of-the-art performance. However, we expect research efforts expanding in areas of knowledge transfer, semi-supervised, and reinforcement learning, since we need a large amount of data, of labeled data for the training, and that requires significant effort. So in the longer term, we see that research efforts will focus on unsupervised learning methods, on methods that they have bring the attention component into the network, and also possible fusion of machine learning and deep learning approaches, which I believe that is called deep hybrid learning. I'd like to thank my students, Sonia, Angelos, Agatha, and Maja. I'd like to acknowledge the support we receive from this organization. And I'd like to thank you for the invitation, and I'd like to thank you for your attention. Thank you very much.
Kostas, thanks a lot. It was really very interesting, and we can see how far, again, we see the deep learning continues to follow and to spread, I think, the coverage of various types of applications of this method. And I would like to encourage participants of this keynote speaker series to raise questions. You can write them into chat, and I'm sure that Kostas is ready to answer them. And I would like you to be active now. You were just passive, and now it's your role to be active. And in between, I will see your questions. I would like to draw your attention to the ISPRS as well, since our society organizes not only keynote speaker series, but also events which for last 2 years had to be only virtual, and now we are going to have a congress which will be in person combined with a hybrid one also, and it will take place in Nice since 6th till the 11th of June. So this is an invitation for you to join us, and I hope that some of you will find an opportunity to come and in person meet not only Kostas, but many other scientists in the society, colleagues, new colleagues, friends, and so on. And this is just my message. And the message comes from the Secretary General of the International Society. My name is Lena Halonova, and I am eagerly waiting for your questions.
Can you try to start your video? You should be able to. Yeah, perfect. Thank you very much.
So I was asked to be shown on your monitors, but this is not important. Your questions and the replies of the experienced professor from Canada are most welcome. That is why we always reserve 15 minutes, at least 15 minutes for the Q&As as part of the session. And I believe there must be some questions. It's, I suppose that all of you, since DL techniques were in the topic, were interested in or are interested. So I have a question regarding reinforcement active learning. Have you compared your approach to letting the expert simply relabel those examples which have the highest error, e.g. according to mean cross entropy across the example? Daniel Gritzner.
Yeah, thank you very much. Thank you very much. We haven't done that with an actual operator doing that. We start evaluating our results, as you can see in this slide here, based on various other methods. And you can see where the mean IU levels is lying right now. So still there is some work to be done on that. And this is
Kostas, we cannot see it.
Oh, sorry. Let me see why you cannot see it. Sorry. Can you see it now?
Yes, thank you.
Okay, sorry, yeah. So what I was saying, so here is we evaluate the mean IOU with the mean IOU during the training. So we had, various methods. We can see here that still our results are not very high as well. And also here is that we can see that this plot, we see an increase in our U for the underrepresented class. But I believe the question was if we had done that with a human, right? So I know right now we examine that with some other methods of doing the active learning. So this is work in progress. So I cannot hear you.
Sorry.
No, okay.
I'm sorry. Another question comes from Jonathan Solorzano. Could you explain with a little more detail what the edge detector used in the UNet for change detection consists of?
So I guess we use the DexiNet edge detector, right? And the whole idea on the edge detector is to able to extract semantic edges. And the reason is initially we try with edge detectors, but we were getting, a lot of edges, let's say from shadows, from corners of buildings, etc., etc. So this edge detector is, when we said semantic edges, is that really edges that describe, let's say the object. Let's say we have, of homogeneous areas that really we have a separation of one area from the other, and that's what we mean semantic edges. And this was trained on the Vehingen data set of the ISPRS, and this was an added branch on the UNet. We had it in order, and that was introduced at the beginning and at the end, so to have this edge information and the features from the edge information be taken into account onto the UNet plus or the UNet.
Thank you. Another question from Getachev Vorkine. I have a question on transfer learning. When you transfer models, how much data you use for retaining the model? Is there a similarity of objects or features on source and target test sites?
We experiment in 3 areas. 2 areas were geographically close, so they had a similar tree distribution, right? So we had the domains were similar, right? And the third side that was quite far, so the domains were not so similar. The tasks were similar because we had the same, we want to detect the same tree species, and it worked. So what we have done, let's say if we go to the second area, we try to do training only from based on the knowledge we had from the first area and apply that to the second, and still, we had some issues. So what we try to do is, let's say, to have 25% of the training data from the other area. So gradually we noticed that we had to use some data and some annotated data from the second area to be able to apply that.
Thank you. And another question from Aidos Makhanov. Can we use extracted Google Earth Engine's RGB geotiff images as an input for training UNet segmentation for crop field delineation?
If you have higher resolution images, yes, you can. Of course, you have to annotate these images, right, and delineate the fields. So you have to create your masks to train that and that could be done in a supervised mode, or you can also, as we're trying to do right now, is to use active reinforcement learning. Although on crop delineation, probably your classes you might not have underrepresented classes there. So it is very important if you have annotated data or not. So if you don't have annotated data, you might try with some of the semi-supervised methods as I mentioned.
Thank you. Another one from Elena Belcore. Dear Professor, many thanks for the interesting presentation. I am newbie in deep learning and interested in the application for trees segmentation. Did the net identifies also the crown borders? how did you segmented the crowns for the training? Many thanks.
We use the crown. So essentially, we created, ortho images, right? And then the crowns were delineated manually. So we annotated, every crown, and then we extract, the individual crown for the 3 species, and these were our training data sets. So that required a lot of preparatory work, and we use, forest experts to help us to identify the trees, and then we did the delineation. We also try to concentrate or to in the delineation to ensure that we were concentrated around the center of the crown, because trees are very dense, and we had, fuzzy borders, right, between, let's say, if one tree is next to the other.
Thank you very much. Another question from Jonathan G. Santiago. What is the main purpose in applying the model stack? Do you train an external model to use the weights of the stack, or how is it though? Thank you in advance.
The idea with the stack generalization, came when we tried to do the 3 species identification using RGB and multispectral data. So we noticed that on the RGB, we had, acceptable results, but using MS, the results were below our expected level. And we got a bit surprised because we had the extra spectral information. However, as I mentioned, there were some issues because on the MS, we had low resolution. So the idea with the stacked generalization is to combine the 2 models, the RGB CNN and the MS CNN, and then try through the meta learning. So that means we take the output weights and we do retraining, and to do retraining and see if we can improve the overall performance. So it's a kind of an ensemble technique that we use with the machine learning. So this work is in progress. I cannot report any results, but we're hopeful.
Thank you very much. And there is one wish from Aidos Makhanov. He would like if you could share your contact, please, in order to get feedback from you for my model.
Sure. Very happy to do so.
Thank you. I cannot see any other question, and time is 4 to 4, and the presentation was planned till 4, so anything is coming, and that's why I would like to thank you, Kostas, very much once again, not only on behalf of me, but on behalf of all participants. And there were more than 90 participants, so it was a great success. And on behalf of ISPRS, for your willingness, for your time you invested for preparation. And I'm sure the participants enjoyed that very much, the same as me. And I wish you all the best, and all of you, and have a nice weekend. Bye-bye.
Well, thank you. Thank you very much. Thank everyone. And if there are any questions, please feel free to email me. I'll be very happy to address any questions.